Hi all, I'm Chris Weishaupt, materials scientist at MAP Laboratories in Everett, Washington. I'm here to discuss some of the challenges that are faced by supply chain managers when they're sourcing new materials and selecting new vendors, and some of the things we can do to help make that process a little easier. This is a particularly egregious case where we were working with a new vendor to order a raw chemical for one of our processes, and just about everything possible went wrong. It's a pretty simplified case, but the early warning signs with this vendor, their response to our questions, and the analytical techniques we use to identify the problem are broadly applicable to not just chemical sourcing, but also resins, coatings, adhesives, etc. I'm mostly going to be talking about this second aspect here, working with often multidisciplinary team of electrical engineers, mechanical engineers, process, reliability, determining what the requirements are for your material and how you're going to accurately determine whether or not your vendor's meeting those requirements. Just to give you some background on this specific chemical, we'd been ordering this 4-hexyl resorcinol as a diol chain extender for a polyurethane that we were developing. It gave it some favorable properties, and we'd had some success, and we were ready to scale up, so we needed a new vendor that we could order multiple kilograms at a time from at a reasonable price. So we ended up finding a new vendor. I'm not going to mention them by name, but there were a couple indications that this wasn't going to work out. One is that the price seemed too good to be true. It was about 15% of the Sigma Aldrich price. They quoted a 6 to 10 day lead time, but then failed to meet that lead time, failed to meet the requoted lead time. Things were not looking good. So a few weeks later, we finally get our material, and what do we find? Well, it's not the pale orange powder that we were expecting. It's a transparent granule, about 1 millimeter in size. It's not soluble in the things it's supposed to be soluble in. It doesn't smell right. The melting point was about right, but it didn't match the melting point of the material we were using before. And then most importantly, it's not polymerizing in our urethane. We're ending up with an excess of isocyanate and a liquid mess at the end of our process. So we did some testing and troubleshooting internally, and we reached out to the vendor with our concerns, and they were not helpful at all. They basically refused to acknowledge that there was any issue with the material. So what do you do at this point? Can we do any better than it doesn't look right and it doesn't smell right? The answer is yes. Fortunately, we had a well-equipped testing lab, so we had a few tools that we could use to determine whether or not this material was meeting its specifications, what it actually was, how pure it was. And my goal is to have you understand a little bit of how these different tools work. Differential scanning calorimetry, usually referred to as DSC, is an instrument where you basically put a small amount of your material, usually 5 to 10 milligrams, into a aluminum DSC pan and have an empty pan next to it, and the instrument measures the amount of energy required to heat up your material compared to that reference pan. You can see phase changes because things like melting the material or moving through glass transitions require extra energy input to keep that heating rate. And then you can see exothermic processes like crystallization when you cool the material. So we ran our DSC on our old vendor and our new vendor. We ramped at about 10 degrees Celsius per minute for the heating and cooling. And the first thing you have to look at when you're looking at a DSC plot is what direction is positive and what direction is negative. And here we have exo up. That means exotherms are positive here and endotherms are negative. Sometimes this will say endo up or endo down. So in this case, we have endotherms going negative. These are melting events, and exotherms going positive. These are crystallization events. The main takeaway here is that the melting point of our new material is 70 degrees C, which is a little bit higher than the 67 of our old material. And then on cooling, our new vendor doesn't crystallize at all when we're taking it to room temperature. The second technique we used to try and determine what this material was and what potential contaminants are present was Fourier transform infrared spectroscopy. Different molecular structures absorb light at different frequencies, and this spectrometer allows you to determine what types of materials are present, what types of functional groups are present, and what types of contaminants are present in a material. In this case, we're using attenuated total reflection, ATR sampling. It's very limited sample prep required, which makes it very quick and easy to run and broadly applicable. You just press your sample against a diamond optic here to obtain your spectrum. FTIR is a very commonly used technique in industry, but there seems to be some mysticism surrounding what it can do, what it can't do, and just how it works. I'm not going to get too in-depth into that here, but I would like to draw back the curtain a little bit and have you understand how it functions. So I'm going to do that by looking at CO2. CO2 is a very simple molecule. It only really has two ways in which it vibrates. It has this bending mode, and it has this stretching mode of the carbon-oxygen double bonds. And it absorbs light near those resonant frequencies for those oscillations, and that happens to be at a wavelength of 15 microns and 4.3 microns. And just one more thing about FTIR spectroscopy that's a little odd for new people is that the x-axis is not in wavelength, rather it's in wave number. That's how many wavelengths there are in a centimeter. And a little bit more on the ATR sampling mode. So this is our diamond optic here. We have a infrared beam bouncing through the diamond optic using total internal reflection. There's a small evanescent wave that extends out into the sample, and that's where your absorbance is occurring for your spectroscopy. There's an equation for the depth of penetration. It actually varies across the spectrum, but it's roughly about 1.5 microns or so. We're sampling a little bit thinner on this side and a little bit deeper on this side. Here I've ran FTIR spectroscopy on the new vendor material and on the old vendor material, and we can see that there's some definite differences between the two. First off, we ran a library search and we found that BHT, a common antioxidant, butylated hydroxytoluene, was the best match. Library searches are a great place to start, but they can be misleading and they can false positive on things, so it's helpful to understand a little bit more about the spectrum. This is obviously a lot more complex than the CO2. There's a lot more peaks, but there's a couple interesting areas in here where we can look. One is that there's a lot more end groups on these butyl compounds relative to hexylresorcinol here. We only have one CH3 group on hexylresorcinol. We have 1, 2, 3, 4, 5, 6, 7 on BHT. And that results in the CH stretching region looking a little bit different. We have this CH3 stretching peak that's much higher relative to the CH2 of hexylresorcinol. So we have the difference here in the CH stretching region. And one other really interesting thing about BHT is this really narrow, spiky OH stretching peak, oxygen-hydrogen stretching. Usually when you're looking at something like cellulose or water or alcohol, the OH stretching will be broad like this. And that's from hydrogen bonding. Hydrogen bonding is when the positive dipole of hydrogen is attracted to a negative dipole, often oxygen. And it basically stretches the bond a little bit. They're electrostatically attracted, and that bond stretching is represented in the FTIR as a widening of the peak. The reason that this OH stretch is so narrow in BHT is that this OH group is kind of trapped in there between these butyl groups. So just physically, it's difficult for this molecule to align to itself correctly for hydrogen bonding. It's just a really interesting physical aspect of the molecule manifesting in the FTIR spectrum. The last technique that I used to look at this material was gas chromatography with mass spectroscopy, GCMS. GCMS typically requires dissolving the material in a liquid. In this case, it was isopropanol. The sample gets injected into, in this case, a 30-meter long column in a temperature-controlled oven. Volatile molecules make their way through the column more quickly. Bigger molecules with higher boiling points take longer to get through the column. So we're separating things and identifying them as they come out with the mass spectrometer. So as the materials exit that GC column, they get impacted by an electron beam that fragments the molecules, and those fragments are analyzed by a mass spectrometer to give us the size to charge ratio. We can see that we have two peaks here. The new vendor was exiting the column at about 7 minutes. The old vendor was exiting the column at about 8.3 minutes. This is pretty consistent with the expected boiling point difference between butylated hydroxytoluene and hexylresorcinol. I have the elution times of the normal alkanes up here for reference, and we can see that those boiling points roughly match. The reason that BHT has a lower boiling point, even though it's a larger molecule, is because of the lack of hydrogen bonding. That hydrogen bonding helps the molecules stick together and increases the phase change temperature. Over here we have the fragments seen by the mass spectrometer. For BHT, we saw 220, which is the molecular weight of this molecule. You got carbon, which is 12 times 15. Hydrogen, which is 1 times 24, and oxygen, which has a molar mass of 16. And add that up, you get 220. This 205 is basically this molecule minus a CH group, or CH3 group. Similarly, with our 4-hexylresorcinol, we get a fragment of 194, that's the mass of the entire molecule, and we get a fragment of 123, which is the molecule minus 1, 2, 3, 4, 5 of these carbons. So that got fragmented off by the electron beam. The data collected from our samples, here is shown in blue, matches the NIST reference spectrum for hexylresorcinol. And for our new vendor, we have this spectrum we collected in red, and it matches this green spectrum from our NIST database. If there had been additional contaminants in here, we would have seen more peaks from the other compounds. And if we zoom in on this butylated hydroxytoluene, we'd be able to see a couple other peaks down in there. GC is a pretty powerful technique because we can both separate compounds and identify. We ended up having a back and forth of emails with this vendor. They eventually provided us with this certificate of analysis that says that it's 99.5% pure. And I don't know how they could call the appearance of that granular material a white powder, but they say that it passes appearance as well. We eventually prodded them a bit on how they're determining this 99.5% purity, and they sent us this. This looks like it was... This is worse than what ChatGPT would generate. This is looks like it was poorly copied and pasted from another document. The instructions don't really make sense. The cast number's wrong. They're running the GC really cold for a material with a boiling point of 300 and something degrees. Overall, this just kind of makes me feel like they didn't actually do any QC on this lot and didn't have any plan for how to do any QC on this lot. One thing worth noting here is that the vendor claims to have used GCFID, that's a flame ion detector, rather than a mass spectrum detector. The FID has really good detection limits and more even response to different types of molecules than the mass spectrometer does. But the downside of the FID is that It's just burning the sample as it comes out of the column and seeing how much material is there in that flame. It doesn't give you any composition information. It only gives you the retention time. So you really need a good reference so that you know for sure that you're matching the retention time to the actual compound you're looking for. And even then, things can potentially overlap. One thing that's done sometimes to determine percent purity by GCFID is to just integrate all of the peaks in the chromatogram. Assume that the biggest one is your analyte and calculate the percentage of the response that's coming from that analyte. So if that biggest peak was 98% of everything that you observed, then you would say 98% pure. But there's a big assumption there, and that's that the most common thing in the sample is the actual compound that it's supposed to be. Fortunately, the repercussions of us getting the wrong material were pretty small in this case. We were still in the R&D stage, so we mostly just wasted some material, we wasted some money, and we generated a lot of hazardous waste that we didn't need to generate. You can imagine how this could have been much worse if the material that they misshipped had been something that reacted violently and somebody got injured, or if it had been something closer to the diol we were expecting so that it reacted similarly enough that we didn't notice it, and then we had bad properties or bad reliability down the road, or something leaching from the device down the road that was unintended. One big takeaway is that there are companies out there that will sell you a banana and tell you it's an orange. I was surprised the first couple times I encountered these types of companies, but I've found that they're more common than I would have expected. The other main takeaway is that we don't have to argue with our vendors about how something smells or how something looks. We have tools that we can use to precisely measure the melting point, to precisely look at the molecular structures present, and to separate materials and look at contaminants present in the material and identify those contaminants. We don't have to rely on fallible human senses. Thank you, everyone, for your interest in this subject. I hope you came away with a little bit better understanding of some of the tools that can be at your disposal for verifying that you're actually getting the materials you're ordering from your vendors.